Okay, this is sample problem 14.6. The decomposition of ethane, C2H6, to methyl radicals, CH3, is a first-order reaction with a rate constant of 5.36 times 10 to the negative 4 reciprocal seconds at 700 degrees Celsius. Calculate the half-life of the reaction in minutes, okay, not in seconds, but in minutes. So the equation is shown, C2H6 is turned into 2CH3. So this is a pretty simple reaction. It's first order. I've written down the relationship between the rate constant K and the half-life T1 half for first order rate laws. So if the reaction is first order, that's when you can use this formula right here. First order. There is a different formula for second order. We'll look at that in a separate problem. Okay. So we want to know what the half-life is in minutes. So let's rearrange this. I'm going to multiply both sides by half-life. So K times half-life equals 0.693. And then I'm going to divide both sides by K. So you get half-life equals 0.693 over K. And we're given the value of K, so we can just put that right in. Now we're not going to get the units that we want in the question, but we'll get almost there. We'll be pretty close to having the right answer. Okay, so we just take this ratio, 0.693, divided by 5.36 times 10 to the minus 4, and you get 1295. Now, what do you think the units are? If you're taking something that's unitless, this right here is unitless, doesn't have any units. Okay, but we have reciprocal seconds. So really what we have is 1 divided by 1 over seconds, which is just seconds. Okay, so there's our answer in seconds. Of course, they want it in minutes, so we're going to divide it by 60. 1295 seconds times 1 minute per 60 seconds. And you get, I guess we should have 3 significant figures here, so 21.6 minutes. Now here's what's nice about half-life compared to rate constant. Rate constant is really, it's pretty abstract. It's a measure of how fast the reaction proceeds. But the half-life kind of makes sense. It's more intuitive. So the idea here would be that whatever our initial concentration is, let's just make it 1 to begin with. The half-life is how long it takes to go to half of that. So down to 0.5 molar. So what they've told us is it'll go down to half that value at 21.6 minutes. Okay. That's all it means. It's how long it takes for it to go down to half its initial concentration. But what's interesting about first order kinetics compared to second is that when you determine the half-life for a reaction, if it's first order, the half-life is constant. It doesn't matter what the initial concentration is. So if we wanted to go down to half of 0.5, which is 0.25, the amount of time it would take to go to that point would be another 21.5 minutes, which would be 43.2, right? So that would go down to 0.25. And then, again, it's constant. So if we wanted to go another 21.6, that would give us a total of 64.8. So we'd be out here, 64.8. That would give us down to another half, which would be 0.125 molar. Oops, not 1.25, but 0.125. Okay, so another 21.6 minutes would get us down another half. And so what mathematically what happens when you have that kind of relationship is you get something called exponential decay. Okay, so this is exponential decay. So if the half-life is constant, and when I say constant, what I mean is it doesn't change with time and it doesn't change with concentration, you get something called exponential decay. And so first order kinetics really do represent exponential decay.